Hello. Okay, let's start it.
Yes, ma'am.
Mm, So we have done linear system with Gaussian elimination
Yes, we've done with
and row
that.
echelon form.
Yeah, yeah,
Remember?
yes. Yes,
Shall we
yes.
start second module?
Yeah, yeah, sure.
Vector space,
Yes, ma'am. Let's start.
because we'll do this like rank of matrix along with another student, because maybe she's taking time, or maybe she's not rejoining after
Okay,
waiting.
okay.
So shall we start second module, vector space?
Yes, yes, we'll start with
Hello?
it. Hello? Yes, ma'am, let's
I
start with
can't
that.
hear you at all.
Now? Hello? Hello?
Can you hear me?
Yes,
Yes,
yes.
now I can hear you. Okay,
Yeah.
so shall we start second module, vector space?
Yes, yes, let's start that.
Okay, so I'm asking, do you know about group, or do you remember set,
Yes, yes,
topic
yeah,
set?
yeah, yeah.
Okay, okay. So let us do it, because we need all of, like,
Yeah.
uh, use set in this vector space.
Okay.
Give me a moment. Can you see the whiteboard?
Yes.
Okay, so topic is vector space. So definition of vector space is, let V be a non-empty set then V is said to be vector space under operation, or you can say under binary operation. Binary operations are addition and multiplication only. If it is satisfied following axioms. Axioms means properties. Following axioms. So, which are axioms? Let us learn. First, uh, closure, closure axiom. Under addition, we'll do five axioms. So, sorry, four axioms, and then we'll do some axioms in under multiplication also. So, first is V1, closure axiom. and we are taking under addition. Mm, what is this? Closer axiom. Let any two element of this non-empty set, let u comma v belongs to this set V, then sum of u and v will also belong to V. Okay, this is closure axiom. Like if we have, like for example, if two like we are taking V as a set of natural number, okay, and 2 and 3 belongs to obviously set of natural number, then 2 plus 3 also belongs to set of natural number. Like for example, we are taking V as a set of natural number. Okay, so you got it. If sum is also belongs to the same set, then we can say closure axiom is satisfied or closure axiom is verified. Got it?
Yes, got it.
Okay. Next is associative axiom. V2 associative axiom. Similarly, under addition, or you can simply write for in a state of under addition, you can just write this symbol only. Okay, for this. Here we will take three elements, and in some book they can use the word associativity also instead of associative axiom. Let u, v and w belongs to v, then u plus v plus w must be equal to u plus v plus w. So if they are equal, then associativity or associative axiom is verified. Next is existence of this is B3 of additive identity. Let a vector v belongs to the set capital V, and this symbol of there exists an element E belongs to V such that V plus E is equal to E plus V gives V only. Then element E is said to be additive identity. Now let us find value of E. Because we have V plus E is equal to E plus V, and that is equal to V. So let us take any two together, either these or either these two. So if we have E plus V is equal to V, then E is equal to V minus V, and that gives E is equal to 0. And so 0 is the additive identity, because when we add 0 with any element, then we'll get the same element. Got it?
Yeah, got it.
Meaning is that there must be zero element in the set. Okay, because means to show this non-empty set to be vector space. So we can conclude it, or 0 be the additive identity. Sorry. Now next, V4, fourth property, existence of additive inverse. Let V belongs to this set capital V, then there exists an element V dash also belongs to V such that V plus V dash gives additive identity. Then V dash is equal to minus, or you can show one more step, 0 minus V, or V dash is equal to minus V. Then V dash is said to be additive inverse of V. Okay. Additive inverse means when we add additive inverse to with an element, then we'll get additive identity. Okay, so this must be in set. When we have any element, then there must be its additive inverse in the same set. Okay, to be vector space. And next, we have two more properties. Next, multiplicative identity. V5, existence of multiplicative identity. Let an element V belongs to the set capital V, then there exists an element E belongs to V such that V into E is equal to E into V gives V only. Then E is said to be multiplicative identity. Now let us find value of V. By taking any one of them, either these or these together, let us find value of E. So we have E into V is equal to V. Then E is equal to V over V, and E is equal to 1. So we can conclude that 1 is the multiplicative identity. Okay, this must be in the given set. which we need to show vector space. And one more property we have to show a given set to be vector space, V6. Sixth property. Distributive axiom or property, you can say. Let U and V, two elements belongs to V, and A comma B belongs to field. Scalar, like V is vector space having like elements as vectors, and this field has element scalar means which don't have direction. You know very well vector quantities have direction also along with magnitude, and scalars only have magnitude like numerical value. Okay, so we have distributive axiom, like first in it, if we are taking one scalar value multiply with the sum of two vector, then we'll get A into U plus A into V. This is left distribution, and this is right distribution. Most probably we show this. Meaning is same. Okay. And third, like if we take sum of two scalar and multiply a vector, then you will get A into V plus V into V. You can show any one of them. Most probably we show first. So just leave it, and you can use this one also. This one only. So these are six properties, okay, which we need to verify in the given set V. Then if all our properties are satisfied by the elements of V, then we can set to be vector space. And just a second. Hmm. One second. Okay. One more property we have V7. Hmm. Scalar multiplication with vector. Let A comma B belongs to set of scalars, means this phi, and V belongs to set phi. Then scalar multiplication we can show as like A into product of scalar and vector must be belong to V, and A into B into V must be equal to A into B into V. Yeah, my mistake. I forgot this property. So this one, V7. Okay, these are property to show any set to be vector space. Okay, I'm checking the next topic. Mhm. Okay, examples and base properties. Give me a few seconds. I'm giving a few examples. And I'm telling you, we mm, I'm telling you, if we have any matrix like having element A, B, C, D, then we can represent this matrix in the form of vector, like taking U is equal to having element as, and V is equal to having elements as. Okay, so we can write any matrix in the in this form. Okay, if we have 3 by 3, then we can write also. Are you getting? Are you getting?
Yes. 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 Getting.
Yeah, yeah. So we can show the set. They'll give you in similar form. Example of vector space, the set R2. R2 means having in a vector. Okay, is vector space. How? If we take like two vectors, let U having element A1, B1, and V having elements A2, B2. Then if we add them, let us find A1, B1, and this is these are also column matrices. Remember?
Yeah.
Remember?
Yeah. I remember. Yeah. Yeah.
Yeah. So if we add them, then obviously result will be matrix, a form of matrix of the same order, because we'll add these elements and these elements, so we'll get the same one. So U plus V will get the same form, A1 plus A2 and B1 plus B2. Means result is, you can say matrix form or you can say vector form of the same number of components. Okay, so we can say like closure property is satisfied if here U and V belongs to R2. R2 means just having two components in a vector, and so we can represent this also a form of R2, means having two components in a vector. Okay, so we can say closure property satisfied. Similarly, you can satisfy the associativity. Okay, because in that case you need to take three vectors here. In that case we need to take three vectors, and after that existence of identity, or obviously we'll have such vector having component 1 1. Okay, so let us do one by one. Mm, okay, my mistake, just right here. First, close up property or close up axiom. Here you need to write. Okay, and here we can say hence closure axiom is verified. Next, associative axiom. Let U, V, and W belongs to this R2, then, and we are taking U is equal to same form A1 V1, or V is equal to A2 B2, and take W is equal to A3 and B3. So let LHS, that is equal to U plus V plus W, that is equal to A1 B1 plus, and this is A2 B2 and A2, sorry, A3 and B3. Let us take here. So we have A1 B1 here, and sum of these two we have A2 plus A3 and B2 plus B3. Now let us add these both also. So result we have A1 plus A2 plus A3 and B1 plus B2 plus B3. Now let us find right hand side. You can take this equation 1, and now let us take RHS, that is U plus V plus W. So A1 B1 plus A2 B2 plus A3 B3. So we have here A1 plus A2, B1 plus B2 plus A3 B3. Now let us them also. So A1 plus A2 plus A3 and B1 plus B2 plus B3. This is equation 2. So you can say from equation 1 and 2, U plus V plus W is equal to U plus V plus W. Both are equal. Hence, associative axiom is verified or satisfied. Next, Existence of additive identity. Of additive identity. Let an element V having component A, B belongs to R2. Okay, let me check. Yes, yes. Then there exists an a zero vector because we are taking this element as a vector in the form of vector, and we must have the same we like having two components in the zero vector, and that must be belongs to this R2 because in R2 we have zero vector also, okay, having two components, such that when we add this V and 0, let us see, AB plus 0 vector gives AB, and which gives V plus 0 vector, or you can say null vector gives V. Okay, so we can say that existence of identity here in R2, or you can say this axiom is verified or satisfied. So we have used 12 pages of this whiteboard, so we need to take now next one. So let me save it. I'm taking just next whiteboard. So existence of additive inverse. Meaning is that if we have any element, then corresponding of the say like in similar manner we have like a additive identity element or additive inverse element, as we have like a vector we are taking having two component in the form of this. So similarly we will need this must be in the same set as we are taking R2. So obviously we have null vector or zero vector in the same. So we can say existence of additive identity is satisfied. Next, existence of additive inverse. Let mm, U belongs to R2, then there exists another like you can take U dash on or you can just use V also, okay, or U dash, or if we are taking alone then you can take V also, not an issue, you can take any like V belongs to R2, and there exists another element V dash belongs to R2, such that V plus V dash is equal to this. So we need to find V dash that must be belongs to R2. So let us find. So we have here V having element A comma B. Let us define here V having component AB, then plus we have V dash having null vector or zero vector component, and v dash we can find, just subtract v from it. So obviously meaning is 0 minus a and 0 minus b. We have this is v dash, and v dash obviously have the minus a and minus b. We can take common, minus common outside. So v dash is equal to minus maybe, and which is, and this is v. So v dash is negative of v, and which belongs to also the given set R2. Hence, additive inverse exists in R2. Now let us take the next, like distributive property or distributive axiom. Okay, next multiplicative identity also. Existence of, you can, or there's no any issue that you show any property ups and downs. Okay, like if you show first additive inverse then additive identity, it doesn't matter. Okay, you can show first associativity then closer, then that is not an issue. Existence of multiplicative identity means, let v any element belongs to R2, then there exists an identity like this in or like in matrix form. You can use this also. This belongs to R such that V into E gives V, such that E into V is equal to V into E gives V. So let us find value of E, and here V having component A comma A and B. So we need to find E, and on right side we have also, then E is equal to having elements 1 and 5, and that belongs to, because we'll cancel them, then obviously we'll get in the form, in the component form. Okay, and with this must be belongs to R2, because R2 have all of the elements having in this form having two components. Okay, having all of the vectors having two components in it. That is why there must be an identity vector also. Hence, multiplicative identity exists. Next, distributive property. Axiom is that scalar quantity belongs to the set field, and vector quantity, like scalar element, sorry, belongs to F, and vector element belongs to set R. Now let us like A. hmm, A is just multiply u plus v, then we have a u plus a v. How? Let us verify that. Okay, first of all, let denote the u and v like this. Like u is equal to having a1 b1 and v having a2 b2. Now to show that a u plus v must be equal to au plus av. So let us do a, and shall I use directly because we have done this a u plus v already. Shall I use
Yeah. Yeah, yeah. Directly.
a1, sorry, a1 plus a2 and b1 plus b2? So obviously a will multiply here a into a1 plus a into a2 and a into b2 b1 plus a into b2. Let us mention equation 1. And now this is LHS, and let us take RHS. RHS is A into U, that is A1 and B1 value of U, and A into V, A2 into B2. So it will multiply A into A1, A into B1 plus A into B, sorry, A2 and A into B2. Now let us add them. Then A into A1 plus A into A2 plus A into B1 plus A into B2. So this is equation 2. So we can conclude from equation 1 and 2. 1 and 2. Uh, A into U plus V is equal to AU plus AV. So distributive properties, first distributive property is satisfied. Oh, second is we need to show this is first distributive property. This is, and we have second. Mm, A plus B to U is equal to AU plus BU. Can you do this yourself or left properties? You need to show in same manner. Can you do them?
Yes, yes, I can do.
So, okay, you have saved whiteboard and also recorded lectures. So, you can do now left properties, okay, by using the
Okay.
same.
Yeah.
Okay. Even if you face any doubt, then you can ask me in next class. Is it okay
Yes,
with
yes, sure.
you?
Yes, yes, okay.
Okay.
Ma'am.
All
Yeah.
right.